Okay, now in our analysis of three regions, we've been able to find the magnitude of the electric and the magnetic field. We've been able to find the reflection coefficient for two regions or for three or more regions. But there's one other tricky thing that we may be interested in doing. If we have region number 1, region number 2, and region number 3, just as before, everything that I have shown you is how to get the electric and the magnetic fields in region number 1. But it's often the case that we would like to know them in region number 2 or even region number 3. So let me show you how to get those. In region number 1, we wrote that the electric field, which is x-polarized, is Ex incident, which we would need to be given, times e to the minus gamma z, plus the reflection coefficient, this is gamma 1 at O1, times Ex reflected times e to the plus gamma z. If we were right here at O1, the value that we would put in here for z would be 0. So at O1, z is equal to 0. Out here at minus d1, if I wanted to find the electric field there, I would put in z equals minus d1. So I'm able to write the electric field any place in region number 1. The magnetic field follows from the equation that we had in the very first set of slides. But if I want to go to region number 2, I need to know something about the transmission coefficient. This is the transmitted electric field. This is in region number 1, these would be gamma 1s. In region number 2, the polarization of the electric field stays exactly the same, and it's going to be Ex incident for region number 2 times e to the minus gamma 2z plus some reflection coefficient, we'll talk about what that is, times Ex reflected in region number 2 e to the plus gamma 2z. Now remember, in region number 2 we had an origin over here at O2. So if we want to know the location, if we want to know the field at O2, then I put in z equals 0. If I want to know the field over here at minus d2, I put in z equals minus d2. So that goes in here, that goes in there. The reflection coefficient that we're interested in is the reflection coefficient right here at O2. So this is the reflection coefficient in region 2 at O2. Remember, we were able to find that off the Smith chart when we looked at Z2 normalized at O2, and we would read its magnitude and its phase. Remember, this is complex. It has a magnitude and a phase. Don't forget the phase. Now here is the only value that I'm particularly concerned about. Right here we can see that we have an Ex incident in region number 1. Let's put region number 1s there just to be more precise. We know that Ex transmitted is equal to Ex incident times this transmission coefficient. The transmission coefficient is 1 plus the reflection coefficient. And in that place, the reflection coefficient is gamma 1 at O1. You can also read the transmission coefficient directly off the Smith chart just by using the different set of lines underneath the Smith chart and the different angles on the top of the Smith chart. So you can either read it directly or you can do just 1 plus the reflection coefficient. So here's our transmitted field. It's Ex incident times the transmission coefficient. That gives us the incident electric field right here, but that's the incident electric field at minus d2. So if I want to get the incident electric field over here at O2, I need to multiply this by the phase shift. So the phase shift is e to the gamma z, where z is going to be d2, and let's talk about the plus signs and the minus signs. Right here is the incident electric field that I need. Right here is the electric field that I had. I can actually look at this equation right here and see that if I had a minus d2, this would be my incident electric field at d2, this would be my incident electric field at O2. So I'm going to use a plus sign with a minus d2 here. So this ends up being minus gamma d2. That will give me the transmitted electric field, which is what I put in here for the incident electric field for region number 2. The same thing is going to happen when I go to region number 3, and I'll be interested in the electric field at O3. But in that case, it's really easy because the transmitted field right here is the field that I wanted at O3. So I don't have to do anything special in region number 3 like I do in region number 2.